Good afternoon, my dear students. My name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering department. Okay, in the previous class, we already discussed the critical thinking questions, mainly derivation of heat dissipation in the long fins, in rectangular fins. Rectangular fins are mainly three types. We discussed in previous class. The first one is the heat dissipation through long pin, heat dissipation through insulated end pin, and heat dissipation or heat dispersed from or heat losses by convection of the end pin. So these three already discussed in previous classes also. Okay, in this class I would like to discuss on critical thinking questions, mainly on effectiveness and efficiency of the fins. We'll see one by one. So you know that the importance of fins. These are the extended surfaces which are added to the main surface, which surface is inadequate to transfer the required quantity of heat. So to enhance the heat transfer rate, we will add some external fins to improve or to increase the effective area. So because Q is directly proportional to area, if the area increases, automatically heat dissipation or rate of heat transfer will be increased. You know this one. Okay. We'll see performance of fin. Performance, it is depend upon the efficiency or effectiveness of fins. Okay, it is essential to evaluate the performance of fins to achieve high heat transfer rate or minimum weight, etc. So fin effectiveness or fin efficiency and total efficiency are some methods used to evaluate the performance of the fin. Okay, so for evaluation of the performance of fins, we have to study about fin effectiveness, fin efficiency, and total efficiency also. So you know this one. This is the rectangular fin. We will see what is the effectiveness. First of all, we will see fin efficiency. What is the formula for the efficiency? What is efficiency? So then what are the formulas for efficiency for long pin and insulated end pin and rectangular or convection of end pin? We'll see. So it is the ratio of heat to dissipation by the fin to heat dissipation takes place when the whole surface of the fin is at the base temperature. Whole surface of the fin is at the base temperature. It means we have to consider the temperature T0. Okay. So it is defined as the rate of actual heat transfer rate taking place through the fin and maximum possible heat transfer rate. So that could occur through fin. Okay. So when the entire fin is at root temperature, is at its root temperature or base temperature. So then we'll get the maximum possible heat transfer rate. So we'll see this formula. The entire fin will be at its root temperature when the material of the fin has infinite thermal conductivity. So you know this one. When the entire fin is at root temperature, automatically the material of the fin has infinite thermal conductivity. So these are the efficiency of long fin. So this is the formula for the long fin. So this one is the insulated end pin or insulated tip pin. So second model, insulated end pin or short pin. Okay. So one more is the convection of the end pin. Here we will see first two efficiency of the long pin. So you know that actual heat transfer by pin by maximum possible heat transfer by that particular pin. Okay. So maximum possible heat transfer occurs at when the entire body is at temperature T naught. You know this one. So Q actual, you know the formula for the heat dissipation or the heat losses by long pin. In previous class, in last class, we already derived this one. That is the under root of HPKA into theta naught. Theta naught is nothing but T naught minus T infinity. Okay. So under root of HPKA A. So here area is different. So T naught minus T infinity. So this is theta naught. You know this one. By maximum possible heat transfer means you know that according to convection formula. So HA into temperature difference T naught minus T infinity. Okay. So here A is the A fin. We have to consider the entire area of the fin. Okay. So this shows the area of the just like end of the fin. So there is a difference AC and A fin. So here we can observe the A fin, area of the fin is the convection heat transfer area of entire pin. So entire pin means perimeter of the pin into length of the pin. So it covers the entire area. Okay. So we have to consider this one. So and if the entire area is at temperature T naught. Okay. So that is the maximum heat transfer by the possible heat transfer by that pin. So if you substitute the values of AC and A fin, okay, then we will get this formula. Here under root HPKA by this is the H into A fin, area of the fin. Area of the pin is nothing but H into perimeter into length. Okay. So here we can write like this one HPL. So here root HP, here HP. Just then we will get that one is the KA by HP root. Okay. So you know this one M is the value is equal to M square is equal to HP by KA, or M is equal to under root of HP by KA. So already for simplification, this term is represented by M. We already discussed in previous class. So this is nothing but 1 by M. So in this place we can write the 1 by M. So this total value is equal to 1 by LM. So 1 by LM. So this is nothing but 1 by M into L. So the final value is equal to 1 by ml or 1 by lm. So efficiency of the long fin, the formula for the efficiency of the long fin is equal to 1 by ml. You have to remember this one. Similarly, so now we will find the efficiency of the insulated end pin or short pin. Okay, here also same formula, actual heat transfer by fin by maximum possible heat transfer. Okay. So actual heat transfer means under root of HPKA here AC into theta naught into, you know the formula tan HML. So this is the entire formula for the heat losses by insulated end pin. Okay, you know this one. Just this is the Q actual, which was already derived in previous class. Then Q maximum, it means maximum possible heat transfer. So that occurs by convection formula. That is the according to Newton's cooling law, HA into temperature difference. Okay, so temperature difference is equal to T naught minus T infinity ambient temperature. So this theta naught to T naught, this will be cancelled. So this entire value similarly same. So that occurs according to here 1 by LM or ML. So anything into 10 H ml. So the final formula is equal to tan H ml by ml. So this is the formula for the efficiency of insulated end fin. Okay. So this is the area. We have to remember this one. Now we'll see fin effectiveness. So that one is the efficiency. Now we'll see effectiveness. Effectiveness of fins. Okay. So because these two terms are used to evaluate the performance of the fin, so we should know about efficiency and effectiveness of fins. Then you can understand the performance of that particular fin. Okay. So fins are employed to increase the rate of heat transfer. So you know that the basic principle of adding up fins is to enhance the rate of heat transfer. So from a surface, base surface, by increasing effective area. So if you add the fin to any surface of the engine, it means the effective area of that engine will be increased. So if the area will increases, automatically rate of heat transfer will be increased. So Q is directly proportional to A. You know this one. Okay. So in the absence of fins, the heat convected by the base area, you know this formula. In the absence of fins, if there is no fin, the heat convected by the base area is equal to HA into T naught minus T infinity. So A is the base area, you know this one. When the fins are present, the heat transferred by fin QF, that can be calculated from the previous equations which are derived in the previous class. So if you consider this ratio, it means taking the ratios of these two quantities means heat dissipation by fin, with fin or without fin. So that shows the effectiveness of any fin. So the effectiveness of fins is defined as the ratio of heat transfer rate with fin and heat transfer rate without fin. Okay. So with fin heat transfer rate, without fin heat transfer rate, we have to calculate this one. The ratio to these two, that shows the effectiveness of that particular fin. Okay. So first we will see effectiveness of the long fin. Effectiveness of, it is represented by epsilon. Effectiveness of long fin. So effectiveness of long fin is equal to Q fin, heat dissipation or heat loss by fin, long fin by, so heat loss without fin. So with fin, without fin. So this is the formula for with fin. So this one already derived in previous class. So under root HP Ka into theta naught. Theta naught is nothing but T naught minus T infinity. So this one shows the Q without fin. So HAR H into EAR theta naught. So theta naught minus here temperature difference T naught minus T infinity. Okay. So this one is the heat transfer rate without fin. So if you observe this one rectangular fin, so this is the surface. For this one, rectangular fin is added like this. Rectangular fin was added like this. Okay. So heat transfer rate. So heat transfer rate with fin. Okay. So this is the fin. So heat transfer rate with fin means Q fin. So this is the formula under root of HPKA theta naught minus T infinity. So that is the Q fin. So if you remove this fin, so the heat transfer rate. So this portion, this area, particular area. Okay. Otherwise this one. So that shows the area ER. Okay. So without fin, with fin. So this particular attached area of the fin. So I have to cancel this one. This area is equal to ER. Then in the previous slide, what was explained in efficiency. In the efficiency, that area is different. Here, this area also different. You have to observe this one. So AC is the same. Okay. AC means end of the pin area. So ER. So here area. So end of the pin area and this area. So both are same. Both are same. So this area and this area. So it means here AC is equal to ER. It means you can cancel the AC with ER. Okay. So then the formula, because this is in root, this is not in under root. Okay. So the formula is like this one. Okay. Under root HP into HPK by, so here just like HAR HA whole square. Just like if you simplify this one, automatically you will get this one. Under root of HP KP by HA. So this is the formula. Under root KP by HA. So because this root H will be cancelled with root H, P, root K, root AC is cancelled with root AC. Okay. So then the value is equal to total root of KP or PK by HAC. So this is the formula. It means you have to understand this. The area which is in efficiency, so that is the different area. The area which is in effectiveness, these areas, both the areas are similar. So end area that is equal to attached area to the base surface. So we can cancel those areas. Then the final formula for the effectiveness is equal to under root of KP by HAC. You have to remember this one. For finding any effectiveness of fin, we can use this formula. Next, effectiveness of insulated end fin. Insulated end fin. You know this heat loss by fin, with fin, or heat loss by without fin. You know the formula. The ratio of heat loss with fin or without fin, and without fin, that shows the effectiveness. So effectiveness for insulated end tip is the Q fin. It means heat dissipation or heat losses by fin. You know the formula for that insulated end is equal to under root HPK theta naught into tan H ml. This is the formula. By same without fin. Without fin means HAR into theta naught. Theta naught means T naught minus T infinity. So this value, this temperature will be cancelled. Then if you simplify this one, this will get this one. So under root of KP HAC into tan H ml. Tan H ml. Okay. So you have to remember these formulas. So we already derived the effectiveness of long fin, effectiveness of insulated fin, efficiency of the long fin 1 by ml, efficiency of the insulated end fin. Okay. So tan H ml by ml. Okay. So these four formulas you have to remember to find the effectiveness and efficiency of your fin. Okay. Now we'll see effectiveness values. If the effectiveness is equal to 1, if the effectiveness is equal to 1 means Q fin by Q without fin. You know this, without fin. Without fin. It means heat loss by fin, by the fin, or with heat loss by without fin. So this is the formula. If this is equal to 1, It means Q fin is equal to Q without fin. So Q fin, so heat loss by with the help of the fin is equal to heat loss without the fin. It means so there is no effect of fin. Fin does not affect the heat transfer at all. So the functioning of fin is negligible. Okay, there is no functioning of the fin. So the fin does not affect the heat transfer at all. So that shows the effectiveness is, if the effectiveness is equal to 1. Now we'll see effectiveness is less than 1. Effectiveness is less than 1 means Q fin by Q without fin. So this is the formula without the fin. It means this is effectiveness is less than means Q without fin is greater than Q fin. It means by the help of the fin, heat dissipation is decreased. So heat dissipation decreased means fin is acting as an insulating material here. So in this case, fin acts as insulation, not conduction material. So that material, that fin has act as insulation. If the thermal conductivity of fin is very low, that means thermal conductivity of that material, that fin material is very low. So if effectiveness is greater than 1, you require this one. So fin is functioning effectively. It means heat transfer will be increased. So Q fin is increases compared to Q without fin. So we required just if you get effectiveness is greater than 1 means fin function is good, then you can understand the performance of that fin also. So some more relationships you can observe here. Effectiveness of fin is directly proportional to 1 by root h. So root h heat transfer coefficient. Effectiveness of fin is directly proportional to root k. If the thermal conductivity increases, automatically fin efficiency effectiveness will be increased. If the heat transfer rate increases, fin efficiency decreases. If heat transfer rate decreases, fin effectiveness will be increased. So you have to remember this one. Then effectiveness of fin is directly proportional to perimeter by area. So we have to remember these relationships also, which are influencing the effectiveness of fin. Now see some important note points here. We can see fins are generally used where convection heat transfer coefficient value H values are relatively low. So in that case, we will use the fins. So when air or gas is the medium, the heat transfer is by natural convection. Know that one. Q is equal to HA into temperature difference T0 minus T infinity. So where the condition where the heat transfer coefficient values are relatively low, then we'll use the fins generally. Fin material should be made by high conductive material because Q is directly proportional to root K. If the material which has high conductivity, then that fins, the performance of those fins functions properly, very effectively. So aluminum is the preferred material because aluminum is low cost and it has good conductivity compared to copper. So it has very good conductivity, but cost is very high. So preferable material is aluminum. So low cost and weight, also less weight, and resistance to corrosion also there, and Thermal conductivity also very good. Okay, so you can see this type of aluminum pins are available on the engine of motorbike engines. Okay, so engine surface of the motorbikes. Next, lateral surface area P by AC of the fin should be high as possible as, okay, because Q is directly proportional to under root of P by AC. Okay, so this lateral surface area should be high as possible as, so as high as possible. Okay, fins with parabolic and triangular profiles, so that contains less material and are more effective, requiring minimum weight. Okay, so this type of geometrical constructor type fins also very influencing fins. You can prefer those fins also. The efficiency of the most fins used in practice is 90%. You can see these are the important points regarding the fins. Okay, so we'll see, we'll solve one numerical based upon the fin, then we will conclude uh, this class. Okay, so find out the amount of heat transferred through an iron fin. So fin is the fin material of uh, the material of the fin is iron. You know that iron fin of length is equal to 50 mm. So length 50 mm means your short length. So it is, we can consider this is the insulated end pin. Okay, L is equal to 50 mm and width is equal to 100 mm. Convert into all meters, and thickness T is equal to 5 mm. Thermal conductivity of iron, okay, that K is equal to 210 watt per meter degree centigrade. So, and heat transfer coefficient H is equal to 42 watt per meter square Kelvin, degree Celsius. Okay. So for the material of the fin, the temperature at the base of the fin. So base of the fin means T naught is equal to 80 degrees Celsius. Okay. So ambient temperature also given, T infinity is equal to 20 degrees Celsius. Assume fin is insulated because short fin, the length is 50 meters. You can consider it is a short fin. Okay. So then we can solve the find out the amount heat transferred through the pin. It means you have to find out the Q. You know the formula for the Q for insulated end, that is the under root of HPKA into theta naught. Theta naught is the T naught minus T infinity into tan H ml. Okay. L, you know that H already given. P is the perimeter. Perimeter is equal to so perimeter is 2 into W plus the thickness. You can consider this one. And the K thermal conductivity also given. Area W into T. You can take that area. And M, you have to find out this one. M is equal to you know that M square is equal to HP by Ka. Then M is equal to under root of HP by Ka. Okay. By using these values, you can find out the M. If you find out M, then you can substitute all the values in this formula. Then we will get to rate of heat transfer. We will see here. Okay. Just okay. So we'll see one more numerical. That is a steel rod. Thermal conductivity of the steel rod is given. K is equal to 30 watt per meter degree Celsius. So 1 centimeter in diameter. So D is equal to, this is the circular type pin. Diameter is equal to 1 centimeter. Convert into meters. And 5 centimeter long. So this one also short pin because 5 centimeter means 0.05 meter long. So from a wall which is maintained at temperature T naught is equal to 100 degrees Celsius, the rod is insulated at its tip. You can consider this one. This is the insulated end pin and is exposed to environment. So that H value, rate of heat transfer is equal to 50 watt per meter square degree Celsius. So this is the value, and atmosphere temperature also given, that T infinity is equal to 30 degrees Celsius. Calculate the fin efficiency. Temperature at the tip of the fin. So temperature at the tip of the fin means X is equal to L place. You can find out the we have to find out the T formula. You know that formula because already in last class we discussed that one. Then rate of heat dissipated. So fin efficiency you have to find out. Efficiency you have to find out. So temperature at X is equal to L value you have to find out, and Q rate of heat dissipation you have to find out. First of all, we will find the fin efficiency. So you know the formula for the fin efficiency for the insulated end. So in my previous slides, you already saw that one. So tan H ml by ml. Okay. So here, first of all, you have to find out the m value. So what is m? M formula is equal to under root of hp by k. Okay. H value given, k also given, p pi d, perimeter, area pi by 4 d square. So you know that values. Okay, then you can, if you substitute the values, then you will get m value. That m is equal to 25.82 meter to the power of meter to the power of minus 1. Okay, inverse. So this is the m value. Then you can substitute the m value. M is equal to this one. L is equal to length also given. That is the 0.05 meters. And all the parameters are given. Then you can find out the efficiency. Then efficiency is equal to tan H ml by ml. If you substitute the values, then we will get the efficiency of this fin. That is the value is equal to 66.54 percentage. You can calculate this one. Next, we will see the temperature at the end of the pin. At the end of the pin means end, it means total length is equal to X is equal to L. You can take. So you know that formula T minus T infinity by T naught minus T infinity is equal to cos H m into L minus X by cos H ml. So this is the formula to find out the temperature of insulated pin at any position at distance x. So here distance x is equal to L. If you take L here, this is the value 0, cos 0 means 1. The formula will be like this one, T minus T infinity by T naught minus T infinity is equal to 1 by cos H ml. Okay. You know the value of M and you know the value of L also, and you know the value of infinity 30 degrees. So you know the value of T naught 100 degrees. If you substitute all the values, then you will get to T value. So the T value is nothing but 65.79 degrees Celsius. Okay. So next last point, you have to find out that one, heat loss from the fin. So you know that formula Q is equal to under root of HPKA theta naught into tan H ml. Okay, this is the formula. So under root H, you know the value, P is the pi d, K thermal conductivity, A is the pi 4 d square, theta naught, T naught minus T infinity, temperature difference, tan H m value also you know, and L value also you know that one. If you substitute all the values, then you will get the heat loss by that fin is equal to Q is equal to 3.658 watts. Okay, so in this way, just we can solve the different numericals which are based upon the insulated end. So these are the different two test books. We can refer to solve different numericals based upon the insulated end fin, which are related to effectiveness and efficiency of the fin. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.